All right, looks like I think we are live on Thursday. And you just saw me scramble through the PowerPoint here. We're going to have probably a short dialogue. I don't know. It depends on what goes on out there and with you guys, and from questions with regard to coordination. I hope everybody had a good Thanksgiving and all that good stuff. Today's topic for a technical Thursday is on coordination. And I know this is, we always talk about selective coordination, and you see a lot of presentations on selective coordination. And if you look in Article 517 in the National Electrical Code, you'll see a terminology of coordination. And even in some of the selective coordination presentations, we'll basically talk a little bit about the fact that selective coordination is not coordination. But I don't know that we've really ever done a deep dive into just the topic of coordination. So that's why the thought process around this technical Thursday. I don't know that it will take us all that long to cover the topic, because really coordination is not that complicated. It's very simple. And Steve Froming, yeah, I know, Froming in the house, and nothing's ever short, right? But that's okay. That's what we're here for. We're here for have a dialogue. So on the coordination front, and the reason I say I think it's going to be kind of short, I mean, the topic is not that complicated, because the whole concept of coordination and the way the code is written sort of takes a lot of the math out of it, a lot of the engineering out of coming up with a solution that meets that either the requirements that are in 517. But again, I'll talk a little bit about ways that you might be able to leverage coordination, but increase the reliability a little bit beyond what the minimum requirement of the National Electrical Code is. So, coordination. I'm not putting a timer on this one either, because I know, you're probably there. If my buddy's out there, Mr. Nihad El Sharif, he'll probably, rib me a little bit about the time. So let's move on. So one of the first things you have to think about, or one of the first, I guess you would say first from a money-saving tips and tricks, is there's no need to calculate fault currents for the purposes of coordination. Again, from a Article 517.1 second perspective, you don't need to know what your fault currents are in the power distribution system. It's a process of comparing curves without regard to the fault current, and we're going to get into that. That means that you won't have to calculate the three-phase bolted fault current all the way down through the system for this process. But again, for short circuit current ratings, for interrupting ratings, there is a new requirement in 408 that says you have to mark the available fault currents on panel boards and things of that nature. You'll probably have to you'll have to at least estimate the available fault current at those areas, but you will not need that for your coordination study. And here's the value of that from a cost perspective. If your fault currents change, remember, if you go back to the videos I have on selective coordination, if you're using circuit breakers, especially circuit breakers, then you are fault current dependent with regard to how you respond when you have multiple devices in series. With a coordinated system, meaning coordination as required in Article 517, you don't have to worry about fault currents. So if your transformers come in at a different size, if your contractor or your electrician decides to shorten conductors up, or put things in parallel, conductors in parallel, your fault currents can go up or down. It doesn't matter, because your determination of coordination wasn't based upon any value of fault current, at least if you're meeting Article 517. So no need to calculate fault currents. I think that's a money saver for you if you're in the from an end user perspective, from a contractor's perspective. The smallest, you can use the smallest, most inexpensive circuit breakers that you can think about. You know, molded case circuit breakers typically have an instantaneous pickup around 10 times their rating. If I'm not worried about fault current and coordinating on fault current, and I'm only worried, and we'll get into the curves, and I'm only worried about that 0.1 seconds and above, then I'm not being forced into a larger overcurrent protected device upstream. Because I don't need, the only reason that I would use a larger overcurrent device, say a larger circuit breaker upstream from another circuit breaker to achieve selective coordination would be because of the fault current. So if I'm not worried about fault current, and that's your biggest factor, if I'm only worried about that long time pickup, and again, we're going to get into the curves, I don't need larger breakers. I can have smaller breakers, which would mean I'll have smaller conductors, I'll have smaller conduit, I'll have smaller panel boards. I won't be into a switchboard as quickly as you might be if you selectively coordinated. Right? So I can reduce the overall footprint size physically too. I mean, if you think about, the conductors are going to be smaller because now I can put a smaller breaker upstream of, say, a 20 amp. I can put an F-150, the circuit breaker, not the truck, upstream of a BAB 30, a 30 amp circuit breaker, regardless of the fault current, where if I was selectively coordinating it, I probably would not be able to use that F-150. It would probably be a larger circuit breaker that may not be able to be adjusted down low enough to 150 amps. So that means my conductor size would be larger, which would mean my conduit size would be larger, which may mean that if I'm into a larger breaker, the original panel board that I wanted to put that circuit breaker in upstream would probably not fit in that smaller panel board, so I'd have to increase the size of the panel board. And since I'm not calculating fault currents, I'm not doing an analysis in that regard with regard to understanding how devices relate to each other with response to fault current. I mean, there are tables which I will show you. We have circuit breaker manufacturers create tables for 0.1 seconds. And I'm just going to, I'm going to throw this over here for you so you can see it. So this is our, I'm going to go up to the first page just so you see what I'm working with. This is our circuit breaker application. So this is the selective coordination breaker application. Now the title says selective coordination, but we do have a 0.1 seconds tables in here. I'm almost positive we do. Oh, no, that's the panel board. Hold on. I gotta grab a different breaker here, a different document. There we go. There it is. This is the one I was looking for. This one is circuit breaker selective coordination tables, and you'll notice there are tables in here for selective coordination, and there it is, table 10. That's what I was looking for. 0.1 second selective coordination chart, which I guess we probably could have used a better term than selective coordination chart, because it's not a selective coordination chart, it's a coordination chart. And here it is. It's actually table 11. Or actually, no. Here we go. Table 9. Table 9 is where it starts. Let me get to the front here, and all right. Table 8D. You'll notice in the selective coordination tables, I'm gonna make this bigger for you, but we in selective coordination, we're worried about the amount of fault current. So what you'll see in a selective coordination table is an upstream and a downstream circuit breaker and a number in the chart which tells you the amount of fault current up to which the upstream will hold its contacts closed and the downstream will open, ensuring selective coordination. And in general, what we would do with from a selective coordination perspective, we would calculate that fault current, the bolted fault current, and compare it with this number that's in this table. And as long as our bolted fault current is less than that number, then you selectively coordinate up to that fault current value. In reality, I'm going to talk about this right before we get done. It could be any current value, right? So I could, from a coordination perspective, I could say I'm going to pick, I'm going to do the arcing fault current. I'm going to coordinate to the arcing fault current. And as long as my arcing fault current is less than this number, then, or the instantaneous pickup of the upstream device, then I coordinate. But now let's take a look at the coordination tables. You won't see numbers in coordination tables, or at least you shouldn't. If you do, I would question the tables that you're looking at. And if you have the right tables, I would question the manufacturer that you're working with. But that's a different question. So in this case here, what we're showing is I can take a 15 amp circuit breaker and coordinate with an F100 from a 100 to a 225 amp thermal magnetic circuit breaker. Now, so keep that in mind. Actually up to a 40 amp circuit breaker will coordinate with a 100 amp F-frame circuit breaker upstream. Now, let's go back to our tables and let's find that same pair with my BAB 34, there's a BAB 40 amp breaker. And I got to find the F frame. Let's go up to the very beginning. There's your K frames, there's your J frames, there's your E. Oh, there we go, F. All right, so a BAB 40 amp circuit breaker. Remember, we'll coordinate with a 100 amp F-frame circuit breaker, but a 150 amp that's a J-frame. I got to get to the right numbers here. F-frame. You know what it is? It's the PDGs. So we're replacing the F-frame circuit breaker with a PDG2. So that's the equivalent of the F-frame, but a new circuit breaker. We will selectively coordinate a 40 amp circuit breaker with up to 1,000 amps. So that what that tells me is, with that same 100 amp breaker, if my available fault, if any current greater than 1,000 amps flows through both of those breakers, based upon this testing, I can tell you they will both open. From a coordination perspective, I can put a 40 amp downstream of that F100 thermal magnetic circuit breaker. And again, I don't have to worry about available fault currents in any case with regard to Article 517 and when I'm doing a coordinated system. So I got Steve roaming. I'm just going to take a look at some of the chats here. Robert from Omaha, thanks for joining us, buddy. Good to see you again, or good to see your notes again. Experiences between knowledge and wisdom, no safety, no plan, no pain, no gain, right? Awesome. David Castro from Eaton, Central America. Thank you for joining, buddy. I appreciate that. What catalog are these tables in? This is on our website. So if you go to the Eaton website, whoops, I'll let you know exactly how I found these. I just go to Eaton Selective Coordination, just Google it, and you could probably find it. Well, let's do this. Eaton.com/consultant. Let's try that. So our consulting engineering resources. If you go to, I never get to it this way, so I'm learning just like you. Power distribution, design guides, seismic calculator education, time current characteristic curve. Let's go to design guides. I don't know if that's where it's at or not. doesn't seem like that's where it's at. Well, let's go back to my original. Eaton Selective Coordination, and you click on, this is the site you want to get to for consultants. We'll have the Selective Coordination Designer. This is a tool that we've created, but I'm telling you, you don't need this if you're doing 0.1 seconds, because it's really that simple. These are your resources. So I downloaded the breaker applications, that's the document that we were just looking at. And then there's an application paper. I believe this, let's just open one of these. It's the application paper. That's the one we were looking at. The industry application, IA 012, blah, 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 all that good stuff. And this is the exact same Word document that I was just working out of, or PDF. So in any case, what you'll see in here from a coordination perspective, let me get back to those tables. I'm looking for a bunch of C's for coordination. Here we go. There's our 40 amp. There's our F100 thermomagnetic circuit breaker. So what this tells you is, now that for that same pair, if my fault current was 4,000 amps, if my arcing current, whatever current, if my current was greater than 1,000 amps and I wanted to make sure the downstream held its contacts, the downstream open while the upstream held its contacts closed, then I would have to put a larger breaker upstream, or I might be pushed into an electronic trip unit, which would increase the cost, right? So that's sort of, from a money savings perspective, coordination actually is a way to save. Now, you may not meet your reliability goals, and we'll talk about that a little bit as we move through this, but you'll see there's no numbers in this table. They're basically just looking at curves, and piece of cake. So because I'm using standard thermomagnetic circuit breakers and just working on the trip curves. Hey, Don Gannier, thanks for joining us, buddy. Talking coordination, buddy. Because I'm just looking at the curves and I'm just looking at the pictures and I'm just saying, I need space between these curves above 0.1 seconds. I'm not calculating fault currents. I'm not comparing their performance with fault currents. I can use these tables all day long. I don't care. It makes life so much easier, okay? And I won't be into electronic trip units, because unless my design says I want to go there, okay? And the National Electrical Code right now does not have requirements downstream for arc reduction technologies. But the reason I say there's limited need is because since I'm not pushing the instantaneous to higher values because of the fault current value, I'm not coordinating to a bolted fault current value. Put it this way, if I'm selectively coordinated to a bolted fault current value to the upstream device, if we think about how I do an arc flash study, I am working in this piece of equipment and I compare the clearing time of the upstream overcurrent device. If I'm selectively coordinating, I'm guaranteed that the arcing current is not going to be in the instantaneous region of the upstream circuit breaker, because the bolted fault current is not in the instantaneous region of the upstream overcurrent device, right? So if I know that as a fact from a selective coordination, for selective coordination purposes, you'll probably want your arc reduction technologies in there to limit damage or to provide worker safety when justified energized work might be being performed on, say, an emergency system. But if I'm in a 0.1 second world where I'm not intentionally adding delays because of the bolted fault current value, the likelihood that my arcing fault currents are going to be in the instantaneous region of the upstream device is probably pretty good. But you'll need to do an analysis from an arc flash perspective to create your labels to make that happen. Now, you're not permitted to coordinate only in an Article 700, 701, 708, 620, or a 645 IT, information technology, what 645 is all about. You can check each one of those up if you're not familiar with 700, 701, etc. take a look and you'll find selective coordination typically in the general requirements area, the earlier parts, if the article has parts. But selective coordination, coordination is not selective coordination. I've got other presentations on selective coordination. We're not here to talk about that. You're not permitted to do what I'm talking about in these systems. 517.30 is the place where I would say this is the only place I have ever seen from an engineering perspective. IEEE does not talk about 0.1 seconds. This was driven, I think, out of I think Florida has 0.1 second that they've historically done. I'm not sure when that was introduced, who introduced it, how it was introduced. I'm not familiar with the background behind it. I understand the concept, and that's what I'm going to help you understand. If we look at 517.30G out of the National Electrical Code, out of the 2020 version, it says overcurrent protective devices serving the essential electrical system shall be coordinated for the period of time that a fault's duration extends beyond 0.1 seconds. Now, that's not a definition, and there really is no definition for coordination in the National Electrical Code. I'm going to show you a NEMA definition pretty soon. Now, the informational note helps you understand you're not really talking about fault currents here. The terms coordination and coordinated, as used in this section, do not cover the full range of overcurrent conditions. And the reason they say that is because all you're looking for is separation of curves beyond 0.1 seconds. You're not considering the fault current. So if I take, this is what you would think of in a time current characteristic curve perspective. I have current across the bottom. So as current increases, my time decreases. That's why they call it an inverse time current characteristic curve. Because as current increases, the clearing time decreases. It's the inverse. Now, you'll typically see what a lot of people refer to, and I refer to, as feet on circuit breakers. It's that, or the hockey stick effect down on the bottom. That's where the blue and the red curve overlap with each other. And typically, SKM, EDSA, Easy Power, and all those other applications will cut those curves off at the available fault current. And if I would say if this was cut off at the available fault current, then your bolted fault current value would be about right there, which would mean it's in the instantaneous region of the upstream device, which if I was selectively coordinating, that would be what my good friend Tim Cernko terms as being ungood. But in the coordination world, it's not a problem because I'm not worried about any fault current that does not extend beyond 0.1 seconds. That fault current will not persist for more than 0.1 seconds. That will open instantaneously. And we could have a debate as to will it open the blue upstream device and the downstream device, maybe just the upstream device and not the downstream device. It could open both. It could open one or the other, but guaranteed, because it is greater than 1,000 amps, which we saw from the selective coordination tables. I know from testing that more than 1,000 amps will open both of those devices. So, because I've done it in a lab, and that's what our tables are based upon from a selective coordination perspective. Now, the arcing current for that 20,000, if you look at the arcing current, it's 13,000, and that was actually 20,000 amps because of you have to look, it's current in amps times 100. Down here on the bottom, you'll see where it says current in amps times 100. So when you see 10, it's 100. When you see 100, it's 1,000. And that current value was marked off at, that short circuit value was marked off at 20,000 amps. And the arcing current value for a panel board with typical spacing on the bus, turns out to be 13,400 amps. So for the very common arcing fault current, both those devices would open as well. Now, from a 0.1 seconds perspective, I don't have to worry about the bolted fault current nor the arcing current, because I'm employing a coordination beyond 0.1 seconds. So only currents that extend longer than 0.1 seconds, which means only those currents that are less than the instantaneous pickup of the upstream device. And so I'm only looking for space between what we would call the overload region of the circuit breakers. Hey, Nihad, I knew you'd be in here, buddy. Good to see you. So, and welcome back to Code Making Panel 2, brother. So, what coordination is looking at, telling you, don't worry about the overlap of curves below 0.1 seconds. Don't worry about the fault currents that are greater than the instantaneous pickup of the upstream device, because we're only worried about technically overload currents. And I can't really say that 100% accurate, because it really depends on what your fault current could be low enough that it's below the instantaneous pickup. And it could be that you've met coordination and you've met selective coordination because the fault currents are so low, but the likelihood of that is also very low. All right, so all I'm looking for is space between curves, and really, all I need is somebody who can draw these curves. If I have a tool, I could buy SKM, I could buy EDSA, I could buy Easy Power, I could just plot these two curves, cut everything off below 0.1 seconds. Don't calculate fault currents. Look for space between curves. It's really that simple. And we've developed the tables that basically do this for you. So this table that you have here that has all of these C's in there that we just talked about, I've already done this analysis to show you what breakers work together, and you can guarantee the smallest overcurrent device. So if you're doing this and you say, I've got a 40 amp breaker, from a cost perspective, you want the smallest circuit breaker you can put upstream and still coordinate to 0.1 seconds, that would be an F100. That opens a lot of doors. Now, if you're looking for some level of reliability from a cascading perspective and your fault currents are at any respective value, or even your ground fault currents, remember, your overcurrent devices are going to respond to ground fault currents as well, and your arcing currents. You have to really think and plan that into your design on whether or not that's what you're looking for. Now, here's a set of curves that this is the BAB breaker, and you'll say, well, that's 0.01 seconds, and it goes all the way down to 0.01 seconds. That curve is not being cut off by fault currents. That curve does not begin to, the foot of that curve, like that red curve has a similar foot to the blue curve. But the red curve is just so fast when the fault currents get high enough that that circuit breaker opens faster than 0.01 seconds. Now remember, one cycle is 1/60. Remember, 60 hertz. One cycle is 1/60th, which is 0.016 seconds. So that means that I am able to open that red BAB 30 amp circuit breaker faster than one cycle. And that's sheerly because it's such a small breaker. The physics, the mechanical nature of it opens it really doggone fast. So that from a coordination perspective, I mean, I go all the way down. I have separation all the way down to 0.01 seconds. So, I mean, I can put a very small, which that's what I'm doing with the F100 breaker. All I'm looking for is separation of those curves. So the only area that I'm worried about in reality is, you might get a blip there. The only area that I'm really worried about is right in here at the knee. So if I'm only worried right here in that knee, and I can take this circuit breaker and make it smaller and smaller. As long as I don't bump into that knee, I am perfectly fine. I will meet the coordination requirements that are in 517. Fuses, very similar. I mean, this is a selectively coordinated. This is a 600 amp breaker fuse upstream of a 300 amp fuse, which will selectively coordinate for up to 200,000 amps. You put 200,000 amps through both of these circuit breakers. The 300 amp breaker, both of these fuses, the 300 amp fuse is going to open and the 600 amp fuse will not, up to 200,000 amps. And I could have if I had a 40 amp fuse, I could have an 80 amp fuse upstream, 200,000 amps through them. I will selectively coordinate. So the desire or the need from now, what a coordination does for you. This is a 35 amp fuse downstream of a 50 amp fuse. I would not be able to use this in an Article 700 system because I have to maintain the ratio of 2:1 between these two fuses to maintain selective coordination up through any level of fault current that goes beyond 1,000 amps, because that's where the blue curve crosses, or just actually up to that where the leading edge of the blue curve, which is let's zoom in on that for you. If I come in on the blue edge there, that leading edge is around, if the big line is 1,000, every line below that is 100. So 1,000, 900, around 820 amps. Anything above 820 amps, I'm going to probably end up in a selective coordination issue, because I would be using the tables at that point, and the tables for fuses tells me I need to maintain a 2:1 ratio, which would mean that in the case of this 35 to a 50, I would need to have at least a 70 amp fuse upstream. But in a coordination world, perfectly fine. In a coordination world, if I zoom in really close on these curves, it don't look it, but I've got space in between these curves and some just barely touching. And there's no guidance in the NEC that says how much space you need in between curves. It's just a guidance that says, hey, you need separation of those curves above 0.1 seconds. So, and this is a 500 amp fuse downstream of a 600 amp fuse that would meet coordination. So as you can see, the world of coordination is, it leaves, I guess the best way to explain it would say it puts more into the lap of the design engineer. Because you could simply take the bare minimum requirement, do 0.1 seconds throughout your entire healthcare system, or anywhere other than an Article 700, 701, or 708. You'll get coordination in the overload region. More than likely, you will not have coordination in the instantaneous region for even the arcing fault currents. But then you might make the argument that, well, my incident energy will be lower in my system, and I don't have to buy complicated arc reduction technologies. I don't need to get into electronic chip units that will give me arc reduction maintenance switch technologies or zone selective interlocking, because the breaker will inherently do it because it's going to open. I'll have multiple breakers open and clear that fault. Again, if you just compare the arcing currents with the instantaneous of those upstream devices, you will be you'll probably be very pleasantly surprised at the performance from equipment damage. And that really gets into, if you think back, a lot of people will talk about selective coordination as an art. And where that comes from, I believe it was Westinghouse that published a book, or it could have been GE, one of the two. They called it The Art of Protective Relaying. And the reason they reference protective relaying is because relays, it's very complicated when you're dealing with these topics, or at least it used to be very complicated in that you couldn't achieve both goals. Because as we said, if I take that blue curve and I intentionally push it to the right, meaning the instantaneous current, the instantaneous pickup is not going to respond to the arcing fault currents or the bolted fault currents, I'm putting in delays. And back in the day when Art of Protective Relaying and those publications came out, we did not have the electronics that we have today. We have differential relaying, we have arc reduction maintenance switch, we have arc quenching technologies that we didn't have back in the day. So today I could achieve selective coordination and give you a system that has minimal damage. It's doable today. Now, you're not going to save money. Not the topic of what we're talking about today, because we're talking about saving you time and money. And saving time and money and achieving arc reduction, achieving equipment limited, reduced equipment damage, and selective coordination is not about saving money. It's about achieving your goals of reliability and minimizing damage. But if I'm looking at getting a system that performs on overloads, I don't care about short circuits. In many applications, I probably don't. I mean, residential homes are not selectively coordinated. Why? If I take the main out, I go down and reset it. I'm not worried about my Article 700 system in my residential home. My smoke detectors have batteries in them. I don't have requirements to have emergency lights in my residential home. If I have an office building, I may not give a hoot whether or not I lose power to the entire facility because I took the main out. I just have somebody go down and reset it, find the problem, and reset the breaker, and people will come back up. No big fuss. People get a little time off during the day, and if I'm not counting productivity in my business goals, then I'm not worried about an outage in my facility. Coordination might be a good option for you. At least you're looking at the long time region, where before you probably didn't even look at that. At least you're looking at some portion of this time current characteristic curve when you leverage and use tables like these. So if you're using this table and you've never used it before and you don't have selective coordination requirements, then at least you know you're coordinated for overloads in those longer clearing time of these trip curves. You've done something beyond what you would have done otherwise. Now, there's an exception in 517.30G, which you see in other things. You don't have to coordinate between the primary and secondary overcurrent devices on transformers because, again, if I take both of those devices out, I take the exact same load. And if I have two devices in series, I don't care if they both open. Even in the overload region, does not matter because I take the same load out. Now, I like this definition that NEMA put together. NEMA says that coordination is localization of an overcurrent condition to minimize outages to the circuit or equipment affected, which is similar to selective coordination. So your concern is minimizing the outage, accomplished by the selection and installation of overcurrent protective devices and their ratings or settings, ensuring separation of their time current characteristic curves beyond a specified time period, which is 0.1 seconds, without regard to fault current magnitude. So that's what we just talked about. But they added this one, or below a specified level of fault current less than the maximum available fault current. And what that does, and now I'll tell you how I used that back in the day. When I would do this with customers that were in the commercial world, they would pay me to do a selective coordination study. I would plot the curves. When my bolted fault current was too high into the instantaneous rate, I did not have the luxury of tables. Just put it that way. So when my fault current was higher than the instantaneous pickup of both overcurrent devices, I didn't have a code requirement that said I had to selectively coordinate. So it was a design decision. It was a customer decision. not mine. I never made that decision for my customer. What I would typically do is I would, in my notes for that time current characteristic curve, I would advise the customer that they do not selectively coordinate and explain the available fault current, the bolted fault current value exceeds the instantaneous pickup of 1, 2, or 3, whichever devices. And I would explain that they could possibly have a cascading outage should a bolted fault occur. And then I would leverage the Red Book. Well, I think it's 141, IEEE 141 or 242. I can't remember the number, but it's the IEEE Red Book. And in that book, they noted percentage values of the three-phase bolted fault current for arcing ground fault currents, which they would say are the most common fault that you will find in a power distribution system. And then what I would do is I would do that math. I would plot that value on my time current characteristic curve, and then I would tell the customer, okay, I don't selectively coordinate, and the likelihood of having a bolted fault current value in your system is low. I could argue it probably never happen in a system that's already up and running, and unless you're doing maintenance and you have the bonding straps and stuff like that, it's probably going to be an arcing ground fault. And then I would plot that one, and I would either tell the customer, look, you don't selectively coordinate, but you coordinate to this arcing fault current value, which is based on IEEE 242, because I would never pull numbers out of my butt on my own. I would always reference an IEEE. If I had an IEEE document that I can reference, that would be the value proposition for me to, as a professional engineer, to say, look, this isn't Tom and his 20 years experience. This is IEEE reviewed, public reviewed, and peer reviewed documentation or book, and as an industry practice, that the most common fault is an arcing ground fault. And oh, by the way, it's 80% of the bolted fault current value. I plotted that, and either you do or you do not coordinate to that value. If they didn't coordinate to either of them, I would then tell my customer, look, if you want a level of coordination, I would give them some options. You could make the changes in your overcurrent devices, change the settings, etc. But so that is basically, and then that would cover a coordination to a lesser value of fault current. I see Mr. Education Power. I gotta look. I've been watching the chats, so let's take a look at the chats. Don Gannier, good afternoon. Good to see you, Don. It seems that coordination is a step down in maintaining power versus selective coordination, but we only use coordination in 517 applications. Does not make sense to me. You know what? I'm not going to pass judgment on it, Dawn. If it doesn't make sense, make a public input. That would be my advice, but I would say that that's what the code says. There may be reasons for it. There may not be reasons for it. And the reasons may be financial driven. I don't know. I haven't been involved as much in the debates at Code Making Panel 15. I think there's some things on the docket this cycle that you have to look and review. I think the argument between selective coordination and coordination gets around the bolted fault current value, and the argument would be bolted fault current values rarely occur, and we could have that debate all day long. But regardless of that, I think that's what's typically what the driver is, and what 517 has done is, instead of electing to go to a lower value of fault current that would be probably more realistically seen in a power distribution system, they basically just said, ignore fault current, look for separation of curves. Right, wrong, or indifferent, that's the way it is. Mr. Nihad El Sharif, thanks a lot. I'm glad to be back on CMP2. Good to have you back on CMP2. You've never left CMP2 in my head, Nihad. You're always in there doing what you do, so appreciate all you do for safety, buddy. So does any of this mean anything of condition of maintenance is not regularly applied? That's a good point, Robert. If I don't maintain my power distribution system, regardless of whether or not I selectively coordinated it or coordinated it, I may not be able to rely on the overcurrent protective devices to respond in a manner that they should. So, yeah. You're right, Dawn. It is under purview of NFPA 99, and then so that's right. That's and I think it was debated again at NFPA 99. There were two public inputs. One public input was, and I, you know what, I have to go back to NFPA 99 and see. I know they resolved them, but I can't remember why. I didn't research it. But NFPA 99 looked at two public inputs last cycle. One said to selectively coordinate, and I think that came from IBEW. And the other, I think, came from an electrical contractor, said to coordinate to the arcing fault current, which is the most common fault current. So that public input, I remember seeing that public input, and I thought it made sense because it's arguably one of the most common faults in the power distribution system. So if you definitely didn't like the bolted fault current value, it would be kind of hard to argue that the most common fault current you shouldn't consider. But we'd have to go back to 99 and see that. Does the age of the device have an effect? No, you know what? In my opinion, that's Robert. Robert, if you look at these trip curves, oh wait, I'm closing screens up, and I don't have to because I have it right here. If you look at these trip curves, there's a band in there, and as long as you maintain, molded case circuit breakers, they're going to hit somewhere on that band, and that's tech. I mean, realistically, it's a pretty fat margin there when you think about the range of currents that you're hitting, and the clearing times. So, and there's conservatism built into there that you'll not see. For example, I'll give you an example. A while ago, I had issues with our zone selective interlocking clearing times that we were portraying. One of my competitors had a faster clearing time, and that's like it's a competitive thing. Was, well, wait a second, how can their zone selective interlocking be faster than mine? And it all came into how we create these curves and the level of conservatism that's put into them. For example, my curve might, and you'd have to look at each of the manufacturers, my curve might cover 50 and 60 hertz. It may cover different temperature values. It may cover single pole as opposed to two pole. Worst case scenarios to give you the longest clearing times. And that's why you end up with some pretty fat bands or longer clearing times than what you actually experience in the field. But you're pretty much going to be in between those bands. And from an age perspective, that's why maintenance is important. If you have a molded case circuit breaker, you need to be turning that handle and then following NEMA AB4. AB4 is a good document, good reference document. Mechanical stress, electrical stress, heat, no heat, etc. does not adversely affect. Well, I would say it depends. If it depends on the condition, and I mean, if you have a circuit breaker that has seen multiple fault currents, I mean, if you read AB4, it'll tell you you'll probably need to take it out and take a look at it. I don't see these curves. At least I don't have the experience to tell you that. Taking a circuit breaker out after 20 years and have to think about where it was located. Okay, a circuit breaker located in my panel board in my basement here is relatively dry, and that's if you don't have frozen pipes and let 48,000 gallons of water pour down over top of them, like happened to me. But for the most part, it's conditioned, air conditioned, low humidity area. That circuit breaker is going to probably last a lot longer than a breaker that's outside in an enclosure, maybe not even rated for the outside, but all things considered equal, that you're applying it per the NEC, all of that good stuff. I don't see it adversely impacting the performance of that device. I mean, especially in a 0.1 second world, you're just worried about the overload region. And look how much space you have in between. Look how much area you have between these two curves. not only is your fault current or your load current's going to be somewhere in this that fat bar, but you've got space in between those curves that gives you even more forgiveness on whether or not those curves actually shift or if something happens, because you're only worried about the overload region. And when it comes to the instantaneous, you think about it, loading effects and things of that nature. If I would hazard a guess, I would say you're probably more concerned about the long time region and not the instantaneous region, because you think about it, a thermomagnetic circuit breaker uses a bimetal, and we all know about thermal memories and things of that nature, especially if you're starting motors and whatnot. But from an instantaneous perspective, short circuit current values, if you hit those puppies you hit these two devices here with 10,000, 20,000 amps, you're in the instantaneous region, there's no stressing of a bimetal because you're not even using the bimetal at that point. I have a video on my YouTube site that shows you a 20 amp, I think it's a 20 amp thermomagnetic circuit breaker. There's I call it the clapper. There's a plunger in there that you're sucking in. There's no bimetal. There's no deformation. You're not trying to bend a bimetal and estimate where did it begin and is it already hot? Is it already somewhat bent? Because on a short circuit event, you don't care about that bimetal. And these curves are applicable around a temperature range. So I don't see loading effect. I mean, if I have a breaker that's loaded, if I have a 40 amp breaker loaded with 5 amps as opposed to a 40 amp breaker loaded up with 20 amps, it's not going to make a difference. Not in these TCC curves. I don't care if you had that 20 amps running for 3 days and then decided to ramp it up. I mean, you're not changing the characteristics of that breaker. I know your buddy Jimmy D does not think much of the coordination rule 517. He really went on a rant at a code changes class when yeah. It gets so what the coordination, the engineer in me, I think the more you know about overcurrent protected devices and how they perform together with each other with regard to current, depending upon how I engineer my system. If, for example, like I said, if I have an area that I go, you know what, I don't care if I lose this power. Like a fire pump. Think about a fire pump. We don't care. We don't care what happens to the conductors. We don't care what happens to the equipment. You want that pump to run. Your design decision is not based upon worker safety. It's not based upon protecting the integrity of the conductors so that they don't overheat and they don't start a fire. You're worried about that fire pump running when you need it, period. So you make these design decisions, and the code permits that. Now, if you think about from a coordination perspective, I may say, you know what, I am more worried about equipment damage. My customer has cost considerations. I might pull 2 circuits to a load from 2 different sources and say, well, there's my redundancy. Now, if there's a problem on this circuit and it takes a cascading event, I have another circuit over here that I can turn on. The chances of both of those having the same condition to trip, I've addressed my reliability in a different way than selective coordination. Now, it'll cost me more money. But I think the other part of selective coordination is in some cases, you may have someone say, I want to do other options, and I can't because you're mandating selective coordination. But unfortunately, because 517 went to 0.1 seconds, there are a lot of design engineers that are going, hey, I'm going to save some money here. I don't want to lose this order because I'm putting multiple circuits because I'm worried about reliability. If the code's not worried about reliability, then I'm not going to take that level on my shoulders and then burden my quote with the additional cost that the customer's not asking for. Unless the customer is truly asking for the reliability, then I'll start considering those other options. So I like the NEMA definition, and I would say to pivot off of this definition, another option, and one that I've used in the past, is that I would, in areas where it wasn't a code requirement, in those areas, I would not make the mind up of the customer on the level of performance of the power distribution system. My goal as a power systems engineer was to help them understand what they have. So if they didn't selectively coordinate, I would look at the most common fault in a power distribution system, which would be the arcing fault current, and tell them whether or not they would coordinate to that value. And if they didn't coordinate to that value, I would tell them they do not have, not only don't they have selective coordination to the three-phase bolted fault current value, they do not have coordination to the most common fault in a power distribution system based on IEEE Red Book, which happens to be this number of, this value of current in that scenario. We could now use IEEE 1584, calculate the arcing current, and say, look, you don't coordinate to the arcing current nor the bolted fault current. So there is a very good chance that you're going to have a cascading event. And then provide them a solution. Say, I can solve this problem if you want to. That can be done under a different work order, and that can be done under a different project. But I would always leave that door open, because my goal would not be to say, hey, you're golden, buddy. You're done. Here are your curves. I tried to educate the customer and educate my client at the time, because I was a consultant, with regard to their level of reliability. And my client often would say we don't care, but there were cases when I had some industrial plants that were worried about reliability that said, hey, I want these areas addressed. And then we would come up with a plan on how to modify the power system to get them the reliability that they need. But remember, from a coordination perspective, if that's all you're going for, you don't care about anything else, you don't need to hire an engineer. Use manufactured tables. You don't need to calculate fault currents. You'll probably not be into electronic chip units, and you'll probably not have to have arc reduction technologies, but you should do the evaluation. Obviously, I highly recommend doing an evaluation to determine your incident energy. And it's always good when our electrical workers can work in a labeled environment, and to Robert's point, in a well-maintained labeled environment. The maintenance 70B, 70E, and the National Electrical Code they're the trilogy of a solution for a power distribution system. Very important in that regard. IEEE 1458. 1458. Hold on. 1458. That one escapes me. 1458. IEEE recommended practice for the selection, field testing, and life expectancy of molded case circuit breakers. I should have known that one. Yes, I'm on that committee. 1458. That's out of the PCIC. That is a good reference. And a lot of what you'll see in there came out of NEMA AB4 as well from a maintenance perspective, but a good document to reference, IEEE 1458. And I would also add that if you are a member of the IEEE and a member of like the Industrial Application Society, I believe a lot of those reference documents, and Nihad, you can correct me if I'm wrong, but I would advise that, don't just go out and join IEEE and IES without doing this investigation, because I get some perks because I work for Eaton, and we have a special agreement with IEEE. We pay them all this money, and we have access to pretty much any of those documents. But I believe as an IEEE IAS member, going to IEEE Standards Explore, you can have access to these documents to download. I think it's a part of your membership. So in any case, that's a good reference from a life expectancy. I also would reference NEMA AB4, and I'd also couch this as any electrical equipment. The life expectancy of any electrical equipment is going to be dependent, which is not something I don't think you're going to find in a document well covered. It's going to be dependent on the environment. I look at my receptacles on the outside of my house in this. I got frustrated one day. I went outside to do some work. I plugged my extension cord in. Nothing worked. I tried to hit the reset button. It would not reset. Every one of my receptacles on the outside of the house, none of them worked. So I had to replace them all. I replaced it with a standard receptacle. I have a GFCI breaker inside the house. But I can't expect, I had a level of frustration at the time, but realistically, that receptacle is in an environment. I can't expect it to last the same amount of time as a receptacle, that same GFCI located inside a conditioned environment. Equipment in caustic, hazardous locations, caustic locations, in and around swimming pool materials, those in and around marinas, you can't expect those to last the exact same amount of time as a product that's in a controlled environment. So always consider the condition in which you're applying the product when it comes to maintenance. And NEMA 70B is another good document. We're in the process of revising that as we speak. If you're not engaged with that, reach out to NFPA, say, hey, I'd like to watch that. Nihad's telling me they're not a part of IAS membership. IEEE Standards Association is the owner of the documents, and they sell all of these standards. Well, I don't know, Nihad, did we at least get a discount if you're an IEEE member? I think you do. I would hope you do, but in any case, that's something that's worth investigating. But even if you're in the world of maintenance, or if you're in a facility, you're in an industrial facility, a lot of these documents your company will probably purchase for you, because it's an essential part of a power distribution system. If you're a consulting engineer, then it's part of your business. Download, buy the product. It's all part of, we buy textbooks. Reference documents like this, I think, are a critical part of your library. That is why they added the WR receptacle requirement, but they too fail over. Absolutely, Dawn. I mean, mine were weather resistant. They were weather resistant, and I understand what the weather resistant. I am very familiar with the wiring device standards and all that good stuff, but I don't care what you install outside. I don't care what you install in a caustic environment. It's not going to last the exact same amount of time as that which you install in a air-conditioned home, right? Or an air-conditioned environment. NEMA AB4 is a free download. If you just Google NEMA AB and the number 4, you will find that reference document. From NEMA. You might have to sign up or sign in or something like that to download. I'm not sure. Again, I come at it from a different angle because I'm also a NEMA member, heavily involved with them. Eaton is a NEMA member. So, there are things that go on in the background that I have access to certain files, like UL files and whatnot, that the general public might not have access to because we've paid all this money up front. And it's all covered. So, but for those of you who are not members of the organization or have not done that same financial commitment with that organization that we have, like with IEEE and others, then you'll probably have to pay on a download basis. But I agree. I don't know what the exact. Oh, okay, Nihad. So if I do a IEEE SA membership, which is $57 more, then do I have access to all of those standards? That's a question for you, Nihad. See, Nihad, he's the man. He's the man. He's like research. He's my research guy in the background. And I know all of you are like that. So that's my advice. One of my advice is, if you're 0.1 seconds in 517 does not mean you have to meet that. That gives you the flexibility to think about reliability and come up with different options. But if you're talking about saving money, you're talking about saving time and costs and all that good stuff, use the tables that I showed you. Look for the C, coordinated, There's assumptions there with regard to the set points. Set it, forget it, go away. You'll use the smallest devices that you could possibly use. You'll probably be in standard thermomagnetic circuit breakers, which would mean you're in smaller panel boards. You'll use smaller conductors overall. Be mindful that if your goals are reliability, then you probably should invest a little time and money, but you don't necessarily have to from a code perspective in some applications. At least for UL, they have a free access to their standards. That's a good point. And in fact, I just learned that, Dawn. I was on a call with UL, and I never knew that was available. I don't know if that's new or not, but they educated me that, hey, anybody, it's just like the NFPA documents. You can get the NFPA document for free. You can get, one of the, I think the reasons around NFPA and things like UL is, especially in NFPA's world, it's adopted by a state, and you don't want to say, hey, I mandate you to follow this book, and then, oh, by the way, you got to buy it, right? So I think there were some all right, so it's 10% discount, Nihad. Thanks a lot, Nihad, for researching that for me. But in any case, there were some restrictions and some questions by some individuals that says, hey, how can you mandate this and then require me to buy it? So they gave the free version online, and apparently UL is doing the same thing. Now, I'll couch this with you. When you look at some of these standards, I mean, as a manufacturer, I mean, I'll sit there and I'll question it, what does it all really mean? Because the way they're written, they probably don't let you print it out. And I can tell you, I've had to print mine out, tab it, reference it, because I'm flipping from page to page. I'm not that good on the web or on the computer with PDFs. I can't do what I can do when I have a booklet in front of me and I have it tabbed and I can flip pages real easily. But in any case, at least you have some of that cleared up. Some just key takeaways. A selectively coordinated system will always meet the requirements of 0.1 seconds. So if you selectively coordinate, you've gone above and beyond a 0.1 second requirement. Coordinated systems may not be selectively coordinated. The reason I say may not be selectively coordinated because it's driven by the fault current, and your fault current may be low enough that that it's less than the instantaneous pickup of the upstream device. And it's coordinated, and it meets selective coordination. Systems that achieve selective coordination exceed the performance of a coordinated system, and that's basically the gist of it. I mean, it's really not that complicated of a method to get some level of coordination. You're following to manufacturer's tables. You don't have to calculate fault currents. Don't necessarily have to hire an engineer because you've got the tables to handle it for you. Each manufacturer will make it easy for you. And I highly advise you, if you're not an IEEE member, especially if you're going to get into, if you're an electrical engineer, you don't need to be an electrical engineer to be a member of the IEEE, but probably your organization. All of the other trades inspectors have the IAEI, and pseudo-contractors. A lot of us are members of the International Association of Electrical Inspectors. I think the IAEI is one of those organizations that puts you right there in the middle as a neutral zone, regardless of whether or not you're a contractor, an electrical inspector, a design engineer, manufacturer, whatever you are. That's a very good neutral organization that seeks to educate. IEEE is focused really on electrical engineers, mechanical engineers as well, but it's very focused on electrical in nature. So, but there's a lot of resources that you'll find in the IEEE. Now, granted, in some of the cases, some of the IEEE papers can be very math oriented and very detailed. So you just want to be mindful of that. You want to be careful. If you're going to purchase a document, just be mindful that it's probably, depending upon what it is, it's probably going to be a very technical document. I would recommend the color books, great reference documents, and those are now going over to DOT standards. I think it's the IEEE 3000 series. of standards. 3000 dot, yeah, it's the 3000 series. So anything that is, this I highly recommend from a power distribution system and education perspective. Let me just throw this over here. This is the IEEE 3001 is power systems design. These, I think, are absolutely absolutely necessary to be in your library from a power systems engineering perspective. You'll not find 0.1 seconds discussed in these documents. You'll have you'll see selective coordination discussed. Because that's when you need the engineer anyway. And in 0.1 seconds, I just showed you, you don't need to hire anybody. You go off of manufactured literature. But they're replacing the color books, and if you're not familiar with the color books, they had a red book, a buff book, a green book. Green book was grounding. The red book was industrial power systems. The buff book was your coordination and short circuit studies. The brown book was systems analysis in studies in general. There was some overlap in those. These documents, downloadable, and you can purchase them. Let's see what the what the dollar amount is. Immediate download $100, so $99. Members pay $78, so there you go. There's your membership discount. If you want a printed edition, $123. I think in today's world, a PDF's probably good enough. For $99, that's not bad. I paid more for my books back in the day. I bought my first set of color books in 1990. It was right when I was graduating, right before. I was actually 89 when I bought them. And I got a set sent to school from the IEEE. But these documents, hands down, there's math in there, but there's a lot of, it's readable material that helps you understand the topic at hand. So you can pick, I don't know if they're probably all $99. I'll just pick another one. Whoa, that one's $260. They're not all $99. This one is IEEE recommended practice for the application of power distribution apparatus in industrial and commercial power systems. What was this one? Recommend evaluating the electric service requirements of industrial. Estimating costs. Recommended practice for the instrumentation and metering. Recommended practice for the design of power system supply lighting systems. Now, the other documents that I'm thinking of are your color books. We'll just look for the red book. IEEE 141. IEEE recommended practice for the electric power distribution for industrial power plants. That's the 1986 version. My personal opinion is I like the 1986 version better than the newer version. That's just my personal opinion. Because they took some things out of IEEE 141 in the later versions that I found very, very handy. Superseded by 1993, active. There's your errata, there's your par, so it's currently being worked on. Access via subscription. Buy the standard. Let's see what this one costs. $209 for the PDF, $234 for the printed edition. It's not cheap. Not cheap. Boy, I gave a couple books away. I had like 3 copies of that because I took a class, paid for the class, and it came with the class. I should have sold the doggone book. I would have known it was that much money, but it went to a good home, I'm sure. But in any case, the color books, there's the buff book, the red book, the blue book, the green book. They're all out there. They're all really good documents, but they're going away. Unfortunately, they're going away. Great resource, though, for you. All right, I'm just looking at comments. All right, so that was my Thursday Tech Talk on coordination. I don't have any other material, unless there's something that you guys want to talk about or you have questions. Hopefully, you got something out of this this session on coordination. And subscribe to the channel. Hit the thumbs up, like, and hit the bell. When you hit the bell, you get notified. So, and I'm going to, I've got a good one coming up on 24087. I'm doing that with David Smith. I don't know if you've ever met David Smith. You probably haven't. He hasn't live streamed with me yet. He's a good, smart, young engineer. And we're going to get him involved with codes and standards. I believe he's got his name in the hat for a code making panel. Hopefully you will see him on a code panel in the future. And more heavily engaged with the electrical industry. He does a lot with code adoption across the country. So you're going to want to sign up for that one. And it is, it's on my LinkedIn site and it's on my Facebook site for registration. I'm probably going to do CEU credits through the Central Illinois division. That's right. They reached out to me. I've got to give him a call back and set that up. So we'll probably do some CEU credits with it as well. All right, everybody. Steve Froming, thank you very much for the feedback, buddy. I hope you enjoyed it. I hope you guys got something out of this. And I hope these holidays find you safe and sound and with people that you love. So, and hopefully all of them and you are safe and healthy. Thanks for joining in. Thanks for spending about an hour and 17 minutes with me for this Thursday's 15-minute Tech Talk. Thanks, Dawn. Thanks, everybody. Take care. God bless. And stay safe and stay healthy. Don't forget, subscribe. Hit the thumbs up. Click the bell. Luis Diego, thank you very much, sir, for dialing in as well. Hopefully one day we will meet in person. Yes. I am talking with Rand and the Central Illinois IAEI, and I believe that that program is going to be there. Mr. Abbasi, thanks for dialing in, buddy. All right. We had a few Code Making Panel 2 members. We had a Panel 13 member. We had a few Code Panel members and a lot of smart people. Take care. I'm signing off. Stay out of trouble. Stay safe. Stay healthy. God bless. Mr. Castro, David Castro, take care. Signing off.